Thanks for selecting this video. You may be a student of engineering or applied mathematics, or you may be an expert in one of these areas. What I will present in this video will be something new, which is not usually found in books on engineering or applied mathematics. My name is Charles DeMatas. I am a retired lecturer from the University of the West Indies, St. Augustine campus, Trinidad and Tobago. The topics I will cover in this video are trusses, electrical circuits, and Kirchhoff's laws. Trusses are studied in structural analysis. External forces are applied, and forces in each member are found. In an electrical circuit, voltages are applied, and the currents in each component are found. You may already know how to do this using Kirchhoff's laws. In this video, we show that a method of analyzing trusses in structural analysis corresponds to a method of solving electrical circuits. This provides a connection between two branches of engineering: structural analysis and electrical circuit theory. Here we give a definition of a truss. A truss is a coplanar system of structural members joined together at the ends to form a stable framework. Usually, analysis of a truss is based on the assumption that the joints are hinged. The only forces in the members are either tensile or compressive forces. No bending moments are transmitted to the joints. All forces are applied at the joints. This is a typical truss that is used in this case as a bridge structure. These trusses are very useful for narrow bridges, and in this case we see a rail bridge here. So it's quite common in rail bridges, temporary bridges also, which are usually narrow structures. And you can see that the members are steel members, and they are connected to each other by hinge joints. These circles here are what are called pins. They go through the intersecting members, so it forms, so you have a diagonal, a vertical, and horizontal members being connected at this pin joint. Below you can see at the bottom, these are horizontal beams that go across the bridge, and these beams carry the load to the hinge joint here. So the external forces are applied at the joints. Okay, you can see the pin joints at the top also. This is another truss structure. This is located in Trinidad. Some of you may be familiar with its location. The vertical members, the columns, are continuous. In other words, there's no hinge at the intersection with the other members. There's no hinge where they intersect with the other members. So this is a continuous member as well as this one. And although this is not strictly speaking a truss structure, under certain conditions it is analyzed as a truss because the forces are considered acting along the axis of the members. In solving trusses, equilibrium conditions are usually applied. These conditions state that the resultant as a vector of the forces acting at a joint is the zero vector. In other words, there is equilibrium at each joint. The forces acting at that joint add up to 0. Now we define determinate trusses. These are trusses with the property that if a balanced set of forces are applied at the joints, the forces in the members can be uniquely determined solely by applying the equilibrium conditions. Here we give an example of a determinate truss. We see here members shown by the straight lines being connected at joints A, B, C, D, and also at the left hand and right hand supports. These joints are assumed to be hinged. In other words, they will transmit zero bending moments. The left hand support is hinged and fixed. It cannot move vertically or horizontally. There's no displacement at this joint, but it's free to rotate. The right hand support is on rollers, so the joint here can move horizontally but not vertically, and of course it is free to rotate. The slope of AB is 3 vertical to 4 horizontal, so it forms a 3, 4, 5 triangle. These members are symmetric about this line and about the center, so these have the same slope. These other diagonals. Now, a balanced set of forces is applied to this truss. You have 9 vertical at B, 3 and 6 at the 2 supports, all vertical forces. Now, these are balanced because the 9, of course, adds up to the 6 and the 3, but it's also balanced in terms of moments. If I take moments about the left hand support, the moment of the force 9 exactly opposes the moment formed by the upward force 6 at the other support. Okay, and you can also take moments about the right hand support. The same result is found. 9 is balanced by the 3 upwards in terms of moments. So when I say a balanced set of forces, I also mean balance in terms of the moments. Now we can go from joint to joint and from member to member and find all of the forces in the members here. Let's do it. For equilibrium at this right hand support, the you have a horizontal member here, so this contributes 0 to the vertical direction, so the 6 has to be opposed purely by this sloping member. So you need to have a compressive force of 10 units in this member. You can work out the vertical component. If it's 10 along this member, it will be 6 vertical, which balances this applied 6 unit force. So you need a compressive force of 10, compression being a push on the vertex, on the joint at the support. Now if you look at the horizontal components, to balance the 10 along the member, you need an inward force of 8 in this horizontal direction. So this member has to have a tensile force of 8 units. Next, we'll go to this joint D. And if you consider equilibrium at T, the member BD is vertical, so there's whatever force it has will not be able to oppose the 8 horizontal or the other force in CD. So the force to the right of D must balance the force to the left of D. So you have to have a tensile force also of 8 units in CD. And of course, you have no vertical forces contributed from these two horizontal forces, no vertical components. So there must be a 0 force in this member BD. This is what is called a 0 force member. There's nothing to oppose any forces in it, so it has to have a 0 force. We'll go to another joint and let's look at this joint B. Let's look at the vertical components. There's a force of 10 units pushing upward at this angle, and there's a vertical force 9 downwards. The component of this 10 in the vertical direction will be 6. So since you have a 9 and a 6 opposing it, you need another 3 vertical. So you need a compressive force of 5 units in this member BC in order to give you a vertical component of 3, which together with this vertical component from 6 here balances the 9. And we can look at the horizontal force, horizontal component at B now. You have, well, the vertical will contribute 0 horizontal component, so you have a 10 here and a 5 on the other side at the same angles. To balance those, you can work out the details. You need a compressive force of 4 units in the top member AB. And let's go to another joint. Let's go to A. Let's look at the horizontal components here. You have a horizontal component of 4 here. AC is vertical. It will not contribute anything to the horizontal direction. So in this member, you need a compressive force of 5 units to balance the horizontal component of 4. Okay, we are using these proportions also. And you can look at the vertical components at A. These must be in equilibrium. You have an upward push from this sloping member. This has to be balanced by a tensile force in this member AC of 3 units. You can go over your basic statics and see, just verify what I'm doing here is correct. Now we can look at the joint C. We look at the horizontal components. To balance the horizontal components from this force of 5 and this force of 8, you need a horizontal tensile force in this horizontal member of 4 units. And you can verify that the equilibrium is achieved at this left-hand joint also. So what we've done here is, given the external balanced set of forces, we have found all of the forces in the members of this truss. So this is what is called a determinate truss. Indeterminate trusses. These are trusses for which, given a balanced set of forces applied at the joints, the forces in the members cannot be determined uniquely from the equilibrium conditions alone. And this is an example of an indeterminate truss. Basically, it's the same as the truss we had before, same support conditions also, but there is an additional member AD here. Okay, in the previous example, you did not have this member AD. So there's just one extra member here. Now, in terms of equations, the equations of equilibrium will remain the same number, because you have the same number of joints, you have the same number of equations describing the equilibrium conditions. However, you have an additional member here, so you have an additional variable. The forces are the variables in this case, so you have one more variable. So you have the same number of equations, but one more variable. So you will not be able to get a unique solution for the forces in the members. Now let's go to electrical circuits. For this presentation, electrical circuits consist of sources of EMF, that's electromotive force, for example, batteries, and also resistors connected by wires. The nodes are the connection between the wires. In our diagram here, these small circles are the nodes where wires are joined. And in this case, you have batteries here, 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 and on the branches there are resistors. For any electrical circuit, the following condition must apply. We call this 1' Kirchhoff's current law. At each node, the total current entering is 0. Here we can consider current entering to be positive and current leaving to be negative. So the net inflow is 0, or you can think of it in terms of outflow. The net outflow is 0. Another way of looking at it is that the current entering equals the total current leaving. In order to solve indeterminate trusses or electrical circuits, when we say solve, we mean find the forces in the members or the currents in each branch. Properties of the material need to be considered. Right? So, whereas for determinate trusses, we can find the forces purely from the balanced set of applied forces. For indeterminate trusses, we need the properties of the materials also. Now these properties these properties are described in Hooke's law, for example, in the case of trusses. Extension of a member is proportional to the force applied to its ends. E is the extension here. This is a constant times the force in the member. And for electrical circuits, electrical components, you have Ohm's law. The voltage drop across a resistor is proportional to the current passing through it. This is given in the familiar equation V equal to IR. In solving electrical circuits, in addition to Kirchhoff's current law, there is another requirement, which we denote by 2', Kirchhoff's voltage law. The sum of the voltage drops across any loop must equal 0. An elegant method of applying Kirchhoff's laws to solving electrical circuits is the method of loop currents. Here the number of loops is equal to the number of branches that must be removed to produce a spanning tree. I'm not going into details of this. I will make videos giving more details of this, but we'll just give an example to illustrate. So let's look at this circuit as we had before. You have your batteries and resistors arranged in this fashion. This is an abstraction of this. We are just drawing the nodes here as these little circles and straight lines to denote the branches. And here we have 4 loops: I1, I2, I3, I4. We think of these as currents circulating around. For example, I1 circulates around this loop here. A loop is just a cycle. The I2, think of this as current circulating around this cycle. I3 similarly, I4 similarly, and these are independent of each other. Okay, you can think of this as being independent of each other. Again, I will make more videos going into more detail on these things. Here we will find the contribution of the loop currents to each branch. First, we give an arbitrary orientation to the branches. By this we mean we put a direction on the edges. These arrows indicate a particular direction. This is what we mean by an orientation of the edges, putting these arrows in. And we start off with I1. This loop current I1, it will contribute a value of I1 to this branch, I1 to this branch. It will contribute I1 to this branch, and similarly I1 to this branch. I'll get to the minus I3 and the minus I2 later as we go along, but you can see here that each branch here has I1 in it, and is plus I1 because it goes in the same direction as the loop here, the clockwise direction. Now let's go to I2. I2 is again in a clockwise direction. It will contribute I2 to this branch, I2 to this branch. Now here, because the I2 is clockwise, it will go counter to this arrow, so it will contribute minus I2 to this branch. Here the I2 follows the same direction as the arrow here, so it contributes I2 along this branch. Next we'll go to I3. I3 will contribute I3 to this branch, I3 to this branch, I3 to this branch. All of these are positive because it's in the same clockwise direction. But for this branch, it goes against the arrow, so it will contribute minus I3. And similarly, I4 will contribute I4 to this branch, I4 to this branch, minus I4 because it's against the arrow, and minus I4 because it's against the arrow here. So we can write the currents in each branch in terms of the variables I1, I2, I3, I4, etc. I4. So it's I1, I3, I1 minus I3, etc. And any current flow that satisfies Kirchhoff's current law can be represented uniquely by a set of loop currents. This is any current flow that satisfies Kirchhoff's current laws. You can see here that Kirchhoff's current laws must be satisfied, because whenever you have a flow into a vertex, you have a flow out, same value out of the vertex also. You have I4 going in and I4 going out, because or if you look at it this way, I4 plus a minus I4 will add up to 0. So you can see that for any setup here, Kirchhoff's current law will be satisfied. For any value of I1, I2, I3, I4 that I use, Kirchhoff's current law will be satisfied. Now I'm claiming that any current flow that satisfies Kirchhoff's current law can be represented uniquely by some set of loop currents. This statement, I will make more videos illustrating why this is so, why this statement is so. But for now we will just accept this. This is the situation we arrived at in the last slide. For each loop, we obtain the contribution of the loop current to the branches around it, and these are the currents we obtained in terms of I1, I2, I3, I4. In the method of loop currents, Kirchhoff's voltage law is applied to each loop. So we will obtain 4 equations in 4 unknowns. The unknowns will of course be I1, I2, I3, I4. And these will have a unique equation, a unique solution, sorry. These equations will have a unique solutions, and we'll obtain the values of I1, I2, I3, I4, and we'd be able to find the current in each of these branches. So we'll solve the electrical circuit problem. So this is the method of loop currents. We now come to the important idea of a Stroop. A Stroop is a minimal indeterminate substructure of another indeterminate structure. We look at this example which we saw a few slides ago, of an indeterminate structure. If we remove two members, we also remove this joint. I'm not showing the joint disappearing, but consider that to be removed also. We are left with this other remaining structure, which is also indeterminate. You can verify it's indeterminate. We remove two more members here, and also this joint. It's just not disappearing, but regarded as being absent. What we are left with is the structure with these 4 joints and 6 members. Now, if we were to remove any single member from this structure, we'll obtain a determinate structure. So this is what we consider to be a minimal indeterminate structure. It's the smallest we can go without losing the property of indeterminacy. So removal of any member from a Stroop results in a determinate truss. Now we consider Stroop forces. These are forces in an isolated Stroop with the equilibrium conditions being satisfied at each joint. Stroop forces do not come from any external applied forces. So these are forces in an isolated Stroop. Isolated means without having any external force applied. And the forces are in equilibrium and entirely contained within the Stroop. Now, such Stroop forces can be produced by pre-stressing, for example, lack of fit. If one member is a little too long or too short, it will create this kind of pre-stressing. So a Stroop can sustain this kind of self-stressing. Notice here, if you look at the equilibrium conditions, each joint here is in equilibrium. The forces are in equilibrium here. You can consider horizontal and vertical components of the forces. You'll see that they are in equilibrium. Now, in my diagrams here, I use negative values for compressive forces, and positive values for tensile members. So tension is indicated by a positive value, compression by negative values. Now, in future diagrams, I'm going to omit the arrows here. In other words, I'm not going to indicate compression or tension, but what will indicate compression or tension is the sign, SIGN, of the force. In other words, positive value of F will denote tension, a negative value of F, for example, will denote compression. So I will, in future diagrams, omit the arrows. I will not indicate compression or tension explicitly, but it can be deduced from the sign of the force. Now, as we said, this self-stressing is possible within a Stroop, but it is not possible in a determinate truss. For example, if I remove one of the diagonals, if I remove a diagonal here, effectively that is putting F equal to 0, because I have 0 force along that direction. So the components in the horizontal and vertical directions must also be 0. So this force and this force must be 0. Similarly, here, these forces in the horizontal and vertical members must be 0. And the force along the diagonal will be 0. So if I remove one diagonal, I cannot sustain forces in equilibrium in an isolated structure. If the structure is isolated, I cannot maintain these internal forces. So this kind of self-straining is only possible in an indeterminate structure, and we are particularly looking at Stroops. In solving indeterminate trusses, in addition to equilibrium conditions, there is another requirement. This is condition 2, compatibility conditions. In any Stroop, the extensions produced by the forces in the members must be consistent with the joint displacements. We can obtain compatibility equations for various types of Stroops. And here I've obtained compatibility equations for the type of Stroop we had before, the rectangular form with the two diagonals. I'm assuming the ratio of vertical to horizontal is h/1, and the area of cross-section of the members are A1 for this member, A2, A3, A4 on this side, A5 this diagonal, A6 for this diagonal. And I'm assuming arbitrary forces here. For compatibility, we'll assume that we have arbitrary forces F1, F2, F3, F4, F5, F6. I'm not interested in any kind of equilibrium at the joints, because you can have external forces which are not shown on this diagram. So we just assume arbitrary forces in the members here. Assuming the members are made of the same material, the compatibility equation for this Stroop, in fact, is F1 over A1 plus F2 over A2 plus etc. H squared F3 over A3 H squared F4 over A4 1 plus H squared F5 over A5, etc. You can look at the form of these. Okay, these two terms here correspond to the horizontal members. These two with the H squared correspond to the vertical, and these correspond to the diagonal members. So you can notice the form of the equation. That helps you to remember these things, and it helps to avoid errors also. I should mention you don't have to spend time looking for the word Stroop in videos or in books or anything, because it's something I made up on my own. Okay, I developed this idea on my own, so until it becomes more widely known, you will not find much of it online or in books. Now, the following example illustrates a method of solving indeterminate trusses that parallels the method of loop currents for electrical circuits. In this example, we have a truss structure. It's supported by a hinge joint on this side, this cannot move horizontally or vertically, and it's on rollers on the other side. This can move, the joint can move horizontally but not vertically. Of course, rotation is possible at these two supports. And we have a loading of 4p at this joint, at the joint F, and a reaction of p vertical here and 3p vertical here. You can verify that these are a balanced set of forces. Look at the vertical equilibrium and also the moments. So if you look at these joints A, B, C, D, E, F, these define a substructure here, which is in fact made up of two stroops. A, B, E, D is a stroop, and B, C, F, E is also a stroop. These are minimal indeterminate substructures. So there are two stroops in this truss. Alright, as I pointed out on the previous slide, two stroops can be identified, A, B, E, D, and B, C, E, F. Now, here we consider the external forces 4p, p, and 3p at the supports, and then we find forces within the truss that are in equilibrium, that create an equilibrium condition. So the forces here will be, I won't go into all of the details, you can work this out on your own. And the negative forces, negative force indicates compression, and a positive force indicates tension. So it doesn't matter also what method you use to find these forces, as long as all of the forces are in equilibrium at the joints. That's all you need, and including the supports also, as long as you obtain. Okay, so when I write -1 here, I mean -1 times p. I'm not writing in p into all of them. I'm just writing the multiple here of p. So again, in structural analysis, what you often do is find a determinate substructure first, which is sometimes called a primary structure, and then you apply the loads to that primary structure and you get the forces in the members. So the primary structure is determinate, so you can find the forces in the members purely from the equilibrium conditions. But I'm not requiring you to use any primary structure here. As long as you can find forces in equilibrium at the joints, that's fine. Any method of doing it is fine. Now we will look at the Stroop forces. Here I have the truss, and for each Stroop we put in Stroop forces. I am using Stroop forces as a multiple of x1 and x2. x1 for this left hand Stroop and x2 for this right hand Stroop. So for this left hand Stroop, the Stroop forces will be x1, x1, 3x1 over 4, 3x1 over 4, minus 5x1 over 4, minus 5x1 over 4 on the diagonals. You can refer back to the slide on Stroop forces and see how I got this. Okay, it's based on the ratio of the vertical to horizontal in the diagonal members. Okay, similarly on this side, Now for this member BE, you have superposition here. The forces add up here. So the Stroop force in this member is x1 plus x2. And then the usual Stroop forces on the right hand Stroop, B, C, E, F. Here we superpose the forces we got on the two previous slides. You had the forces in the members from the external forces, and then I have added to those the Stroop forces. Okay, the x1 plus x2, the three x1 over 4 plus the other force, and so on. Okay, so for example here there are no Stroop forces, so these are just the forces induced by the external forces. But for the within these Stroops you have both the forces from the applied loads plus the Stroop force. So you have these in all. So what I'm saying here is that any set of forces satisfying the equilibrium conditions correspond to a unique set of Stroop forces. And next we need to know the cross-sectional areas of the members. I am using these values here, A2, A2, A2 for the vertical members, A1, 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 A1 for the horizontal members, A3, 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 A3 for the diagonals. So once I know these cross-sectional areas now, I can write down compatibility equations for the two Stroops. For the left-hand Stroop, I have to use these cross-sectional areas A1, A2, and A3. Right, vertical, horizontal, diagonal. And these are the forces in the vertical members. In the horizontal members, in the vertical members. These are the forces. You can refer back to the previous slide to see how I got these. Similarly for the right hand Stroop, these are the cross-sectional areas in the horizontal, vertical, and diagonal members. And I times the corresponding coefficients, of course, and together with the forces in the members. So I have two equations, and I also have two unknowns, x1 and x2. So these are compatibility equations that can be satisfied, that can be solved, and which will give a unique set of values for x1 and x2. Once you have the values of x1 and x2, you can find all of the forces in the truss, and basically that solves the truss. So what we have just done is give an example of the method of Stroop forces for solving trusses. And I just want to illustrate on this slide the correspondence between the two things, the method of Stroop forces that I just gave and the method of loop currents, which is used in electrical circuit theory. In trusses, you have indeterminate trusses. In electrical circuits, you have, well, electrical circuits. For trusses, you have equilibrium conditions which must be satisfied. For electrical circuits, you have Kirchhoff's current laws which must be satisfied. So you have equilibrium of currents in electrical circuits. For trusses, you have compatibility equations which must be satisfied. For electrical circuits, you have Kirchhoff's voltage law which must be satisfied for each loop. In trusses, you have Stroops. In your indeterminate trusses, you have Stroops. In electrical circuits, you have loops, which determine loop currents. In our Stroops, we have corresponding to that Stroop forces. So here I am making a connection between two branches of engineering: structural analysis on one side and electrical circuit theory on the other side. More examples of Stroops. These are also minimally indeterminate. Remove any one member from this structure here and you'll get a determinate structure. This is also a Stroop, and of course you can see the pattern here and extend it further. Removal of any single member here will result in a determinate truss. Okay, just remember where the members cross there's no joint. Well, sometimes it's put in, they make a joint out of it, but there's no need for a joint in where the members cross. These are other kinds of Stroops. Here it's a trapezoidal shape. The width at the bottom is L, and it's at the top, it's moved inside, the top joint is moved inside a distance KL. The top joint is moved inside the distance KL. The height here is H times L, so the ratio of vertical to horizontal is H to 1. And because of this, you have different kinds of Stroop forces here. If you have F here, you'll have F over 1 minus 2K here. Similarly, this multiple of F on that side, this multiple of F on this side. On the diagonals, you have negative this multiple times F and negative this multiple times F. Notice the diagonals have equal force here. The positive indicates compression and negative indicates tension. But of course, the F here could also be positive or negative. So for a negative F, the signs will change. Okay, as you change the sign of F, the member will change from either compression to tension or vice versa. This is another type of Stroop. It's a quadrilateral also. The two angles at the base are right angles. But again, you have two diagonal members. The bottom width is L. This vertical height is H1 times L. And the height on this side is H2 times L. Okay, and these are the Stroop forces. You have F at the bottom, H2F here, H1F here. This multiple of F and these multiples of F on the diagonals. Again, on the diagonals you have negative values. On the outside you have the same sign, but on the diagonals the sign is reversed. So if you have compression on the outside, you'll have tension on the inside, and vice versa. Now, in structural analysis, you will come across what is called the flexibility method. It's usually ascribed to Maxwell and Moore. Maxwell, of course, is the famous mathematical physicist. Moore was an engineer and contributed a lot to structural analysis. And what I've given here as the method of Stroops is a variant of the flexibility method, because the Stroop forces ensure that there is equilibrium at the joints, and the compatibility equations impose the condition of compatibility on top of the equilibrium conditions, and that solves the truss. I'm doing continuous work on continuous beams, also frames and 3D Stroops. Extending this work from trusses to beams where I consider bending, frames and 3D structures. Now, what impact will my work have here? I've introduced a new idea, the idea of a Stroop, and developed this idea of Stroop forces and method of Stroops to solve trusses. What impact will this have? Will this make things very much easier for engineers? In practice, it will have very little impact, because everything nowadays is done using software, and my method of Stroops will be okay for someone doing hand computation, but I think the days of doing hand computation are over now. You may have to do it in courses in engineering at university. It's only at school you may be forced to do these problems of finding forces in trusses by hand. So in that case, the method of Stroops may be of use to you. But later on, if you're training for work as an engineer, it's mostly software you will be learning. So I'm trying to reach people at an early age before they reach this stage of learning software. I want to introduce these ideas because I think it gives students a better grasp of concepts in structural analysis. The work I've presented in this video, it draws from the work of other giants which I've stood on. First of all, Gustav Kirchhoff, famous German physicist and mathematician. Very interesting life story. You should read about his work. Very interesting. Also, very interesting and brilliant mathematical physicist James Clerk Maxwell. From a very early age, he was deeply involved in mathematics and physics. You should read about his life also. I would also mention Hassler Whitney, because in mathematics I am interested in a topic called graph theory, and Hassler Whitney is an American mathematician. He came up with the idea of matroids, and it's some of the matroid properties that have guided me in my research into Stroops. Another person that influenced me is Stephen Crandall. A few years ago, when I could not come on to the university, I just had to rely on books on my bookshelf. I picked up this book from my bookshelf by Crandall on engineering analysis, and this led me to think about these equilibrium problems, for example trusses, and led me to the idea of Stroops. This is the basic idea of drawing that I've used for obtaining the compatibility equations. I consider for my simple Stroop here, rectangular Stroop, I consider this joint as fixed. Think of this as the origin, and think of this joint as being capable of movement only along the x-axis. These joints can move horizontally and vertically, and then by looking at the extensions in the members, comparing them with the displacements, I obtain the compatibility equations. I'm not giving all the details here, it will take too long. Just a few quotes to end with. The task is not so much to see what no man has seen yet, but to think what nobody has thought yet about that which everybody sees. Arthur Schopenhauer. All truths are easy to understand once they are discovered. The point is to discover them. This is from Galileo Galilei. Why am I ending with a maze here? Well, prior to working on Stroops, I was working on mazes. After this, I turned my attention to Stroops. And surprisingly, some of the ideas from mazes carried over to Stroops. And the connection comes in the topic of matroids, which I mentioned in connection with Hassler Whitney, the American mathematician. So you often find things that link together in strange ways when you are doing mathematics. Thanks for reaching this far in my video, and I invite you to follow me also on other videos. I may extend this video to another video and go back and look at the basics of electrical currents and explain further the details of loop currents. Thanks again, and again I acknowledge my obtaining support from the University of the West Indies, and hopefully I will obtain support from other donors. Thanks for viewing.